In this class, besides just looking at the concepts of subspaces and spans, we're going to be touching on two really important issues having to do with vector spaces in general. In fact, there are two concepts that relate to all of linear algebra, and I'm going to mention them as we meet them. So first of all, let me tell you what the general issue that we're going to be looking at is. So what happens is that in many situations there are vector spaces that have inside them some smaller vector spaces nested inside. So if we represent a vector space, a generic vector space like this set, of course we're going to need also the two operations, etc., but just graphically to represent it in this way, then inside there might be some smaller sets which actually also behave like vector spaces. And so what we're going to be looking at is a situation where we're dealing with the same types of objects, because of course the smaller space consists of objects of the larger space, so the same kind of objects, just fewer. Okay, and also we're going to be having the same addition and scalar multiplication. Now, to make things a little bit more formal, because of course we're talking about abstract algebra here, so we have to focus very much on what we're talking about, and it helps if we have some formal, very precise definitions. So here is what we mean by a subspace. So a non-empty subset W of a vector space V is called a vector subspace, or in order to say words, just a subspace of V, if what happens is that it satisfies, that's the subset, satisfies all vector space axioms, but by using the same operations as the big space. So all we're doing is we're just throwing away some of the elements of V and keeping only a fewer ones, the ones that we're actually interested in. Okay, so it's basically just the idea of a subset. Take a small piece of it, but as long as we do it in such a way that all the axioms continue to be maintained. It turns out, in fact, that if this is the situation we're in, so a larger space and a subset within it, we don't actually need to check all 10 axioms. And the reason for that is that if we know that the large space is a vector space, then of course the algebra and the specialty axioms will certainly work, because they just come from the algebra, the way the operations work. Okay, so everything is going to work fine in terms of those 8 axioms. So the only ones that need to be checked are, in order to see if a subset is in fact a subspace, it is sufficient to check that it satisfies the closure axioms. Remember, those are the only two remaining axioms. And just as a reminder, the closure axioms are these two. First of all, it's the closure with respect to addition. So that says if I have two vectors in this subset, when I add them up, I must end up with another vector which is still in the same subset. So I cannot move outside of that subset. It has to be closed with respect to the addition. Same thing with respect to scalar multiplication. If I pick a scalar and a vector in the subset and I multiply them together according to the scalar multiplication rules, then what I end up with must be something which is still in the subset. Again, we cannot get out of that subset. If we do, then it's a nice subset, but it's not a subspace. Now, this may be time to mention the first of the two properties that I was alluding to earlier, and that is the fact that one important idea about vector spaces in general is to see in fact how the structure is inherited by the subsets. One of the important things that people look at is, given a space, a vector space, well, how many subspaces does it have? What kind of subspaces does it have? And this sometimes tells us quite a bit about the structure itself of the vector space. So this is a very important issue when it comes to vector space, an important item of research. The second one is what I'm going to bring up in a second in the next slide. Now, remember that in order to check whether a subset is a subspace, all we need to do is check the two closure axioms. Well, if you think about it, and actually I want you to think about it because I'm going to leave you with a little bit of a little task for you to do, is that there is another axiom which we can use instead of those two. So what I want you to do is I want you to prove that the two closure axioms together are in fact equivalent to the linear combination axiom. Now this is an axiom that I have not mentioned before, so here is what it is. This axiom says, alright, so we are in a vector space. What the linear combination axiom says, in order to be satisfied, we have to work like this. Given any two vectors in the vector space and given any two scalars, so just any two real numbers, then the linear combination C1v1 plus C2v2 still has to be in the vector space. Okay? So in other words, if I take a linear combination of any two vectors, I must still come up with a vector in the vector space. Okay? So what I'd like you to do, your task is to show that if the two closure axioms we've seen so far hold, then this axiom is or this property in fact is satisfied, and on the other hand, that if this property is satisfied, then both of the closure axioms hold. And so that means that those two axioms together are equivalent to this linear combination axiom. Now remember, the two closure axioms are very vital, are very, very important, not only because they're two of the 10 axioms, but because by themselves, again, tell us the information about subspaces and the relationship that holds between the initial vectors, the ones that we start from, and what we come up with from the operations. Okay? And so that tells us, once again, the linear combinations are an important, vital part of vector spaces, just like they've been an important part of linear algebra so far. Another reason why we want to look at this particular axiom is sometimes instead of checking both closure axioms, it may be faster, easier, just more convenient to use this one axiom. It's just going to allow you to take a little bit less time.